I want to discuss with you today the origins of osmotic pressure. I think that too often we get down the path of doing math and looking at empirical data like how much the water rises up without really breaking down what's happening. This is really similar to the ideal gas law. And so I want to go back and discuss the ideal gas law briefly. And I think in doing so, we can then transition to osmotic pressure and have a clear understanding of what we mean by that. Look, if I write this ever so popular equation, PV equals nRT, we know it by memorization, but we also recognize that it makes sense, especially if we reorganize this to talk about pressure. And so pressure equals the number of moles divided by the volume times some constant, the ideal gas constant, times temperature. And when we write it like this, hopefully it makes more sense. Where does pressure come from? Well, pressure comes from on a container wall, the molecules are going to bounce off. And when the molecules bounce off, there's a change in momentum, and that change in momentum gets put onto the wall, causing pressure. So clearly, the more of these collisions I have, the higher the pressure. Well, how do I know how many of the collisions I have? Well, how many of the collisions I have is related to how many atoms or molecules I have in the volume allotted. And if I put more stuff in a smaller space, that makes higher pressure. So that part of the equation makes sense. Then, of course, the harder these things run into the wall, the more pressure it makes on the wall. Well, how hard are they running into it? Well, the hotter they get, the faster they go. And the faster they go, the more momentum they have when they run into the wall. And so clearly temperature is a factor there. If I increase the temperature, I'm increasing the strength of these collisions and increasing the pressure. So now let's transition to talking about in a solution. If I have a bunch of water, I draw water as these little V's. Hopefully we recognize that that is water, and I can just abbreviate it as a V. And so I have a bunch of water surrounding, and we know waters kind of like each other. You have this hydrogen bonding, so they're not necessarily trying to fly apart from each other. But, if I stick something in there, like let's just stick a sodium ion in there, sure, it's stable within the water. The water will reorganize to take the negative side of the water and orient it towards the ion and stabilize the ion. And hopefully some of this is familiar to you. But if another sodium ion comes along, it's going to repel. They're going to want to repel each other. They're going to want to move apart. This is the exact same thing that happens in a gas. The reason that a gas is that all the molecules are repelling each other, or all the atoms are repelling each other, and that causes them to move apart from each other. So when they bump into each other, they fly back apart, and they keep bumping into each other and flying back apart. And when they run into the wall of whatever container they're held in, it causes pressure. Well, these sodium ions in solution are no different. They're moving around and they're running into each other and flying apart. And then you would say, well, what about the chloride ions if it's sodium chloride? Well, they run together and they stick together. That's not true, because we know sodium chloride dissolves in water. And because they're stabilized by their water, remember the hydrogens would all orient themselves around the negative chloride ion, and it's happier being surrounded by water than bonding with the sodium. That's why it dissolved in the first place. So when these things run into each other, the sodium and the chloride ions, they also bounce off of each other. Well, hopefully that reminds you similar of what the pressure is in a gas. And remember, the pressure in the gas depends on the number of things there are present. Well, this is no different. If we write the equation for osmotic pressure, pi equals iMRT, look, it's really the same equation. Pi is osmotic pressure, that's just P. And the RT's line up. So what we have to explain to ourselves is how is this IM equal to N over V? Well, M is molarity. M is the number of moles in 1 liter of solution. Recognize it's the same units. This is the number of moles in 1 liter of the container. So that part makes sense. Then the I piece also makes sense. In a gas, N is the number of molecules. In the solution, we get a little mixed up because we say, for example, NaCl dissolves in water. And we can think of this NaCl as one thing. Of course, that wouldn't be appropriate in any context, because even if we talk of NaCl as table salt, it's a lattice, a crystalline lattice that goes on and on essentially forever. It would be a sodium attached to a chloride, and it would go on forever and ever. So this is never really one thing, but we could think of its formula and say, well, sodium chloride is written together, so we think of it as one thing. But clearly when it dissolves in water, it becomes Na plus and Cl minus. So when it dissolves, it becomes two things. So we have to account for that. And so the I, if it was sodium chloride, I would be a 2 because we have twice as many things as we do per formula. And so hopefully that helps explain where the origin of osmotic pressure comes from. But then practically, we have to be able to explain it, because it's not like the water is trying to explode out of its container because the pressure got too high. So what do we even mean by pressure? Because if I increase the pressure of a gas in a cylinder, we know what that means. If I increase it too much and the cylinder's not strong enough, it can get dangerous. It can explode. We think of scuba diving tanks and things like that that can get quite dangerous. Well, osmotic pressure doesn't make a dangerous pressure, but somehow we have to make sense of why we call it pressure at all. Well, look, let's imagine a situation where I have a beaker of water, and then I'm just going to connect it by a tube to another beaker of water. I'm going to fill this one up with a solution of, let's stick with sodium chloride because that's the one I think we're all most familiar with. So it's got sodium ions and chloride ions. And of course, it's got many, 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 many sodium ions and chloride ions. So many, the mind cannot even fathom it. And now I take another solution, and let's just fill it up to the exact same level. And over here, I just have pure water. And I put my membrane in right here, which is my semipermeable membrane. So it allows water to go this way, but it does not allow sodium or chloride ions to go the other way. It's not allowed. We're going to kill that. And so what would happen in this situation is that we could imagine that these ions are all trying to fly apart from each other. And as they're trying to get away from each other, of course, they can't jump out of the water. They're confined to the volume of the solution. But what they can do to move apart from each other is suck water through this barrier. Because remember, water can go through. And as more water comes in, these things move further and further apart, alleviating the pressure. Well, that kind of makes sense. And of course, if we did that, this water would go up in volume and this water would go down in volume. But I'm going to propose that we modify this experiment. And I'm going to put a disc on the top of this water. And that disc is going to be sealed to the beaker. So now I got a disc right here that is sealed to the beaker. Maybe we got an O-ring seal on the edge of this disc. And so it's sealed there. And then I'm going to put an arm on this. And I am going to push down with some force. I'm going to push down on this with some force. Now, as the water is trying to come through the semipermeable membrane and expand this solution, I'm going to push down with a force, putting a pressure on the solution. And it turns out if I push hard enough, I can stop the water from coming through the membrane and expanding this solution. The pressure from this force that's necessary to stop the water from coming through this membrane is the osmotic pressure. Make sense? I think it does. And of course, if we want to talk about pure water, and you're familiar with water purification, there's a process called reverse osmosis. And all that means is that I'm going to put so much pressure on this solution that I force water the opposite way through the membrane. And remember, the ions can't go through the membrane. Water can clearly go either way through the membrane. It's just which way is the force pushing it. So if I put enough force on this, I can push the water through the membrane this way, and then I'll get pure water, and I can take the salt out of the water, and that'd be reverse osmosis. Hopefully, that clarifies some things for you, and you can kind of imagine osmotic pressure before we get into the math.